Section 14 of Climatic Changes, Their Nature and Causes by Ellsworth Huntington. This LibriVox recording is in the public domain, recorded by Leon Harvey. Chapter 14. The Effect of Other Bodies on the Sun. If solar activity is really an important factor in causing climatic changes, it behooves us to subject the Sun to the same kind of inquiry to which we have subjected the Earth. We even inquired into the nature of the changes through which the Earth's crust, the oceans, and the atmosphere have influenced the climate of geological times. It has not been necessary, however, to study the origin of the Earth, nor to trace its earlier stages. Our study of the geological record begins only when the Earth has attained practically its present mass, essentially its present shape, and a climate so similar to that today that life as we know it was possible. In other words, the Earth had passed the stages of infancy, childhood, youth, and early maturity, and had reached full maturity. As it still seems to be indefinitely far from old age, we infer that during geological times its relative changes have been no greater than those which a man experiences between the ages of perhaps 25 and 40. Similar reasoning applies with equal or greater force to the Sun. Because of its vast size, it presumably passes through its stages of development much more slowly than the Earth. In the first chapter of this book, we saw that the Earth's relative uniformity of climate for hundreds of millions of years seems to imply a similar uniformity in solar activity. This accords with the recent tendency among astronomers, who are more and more recognizing that the stars and the solar system possesses an extraordinary degree of conservatism. Changes that once were supposed to take place in thousands of years are now thought to have required millions. Hence in this chapter we shall assume that throughout geological times the condition of the Sun has been almost as at present. It may have been somewhat larger, or different in other ways, but it was essentially a hot, gaseous body such as we see today, and it gave out essentially the same amount of energy. This assumption will affect the general validity of what follows only if it departs widely from the truth. With this assumption, then, let us inquire into the degree to which the Sun's atmosphere has probably been disturbed throughout geological times. In Earth and Sun, as already explained, a detailed study has led to the conclusion that cyclonic storms are influenced by the electrical action of the Sun. Such action appears to be most intense in sunspots, but apparently pertains also to other disturbed areas of the Sun's atmosphere. A study of sunspots suggests that their true periodicity is almost, if not exactly, identical with that of the orbital revolution of Jupiter, 11.8 years. Other investigations show numerous remarkable coincidences between sunspots and the orbital revolution of the other planets, including especially Saturn and Mercury. This seems to indicate that there is some truth in the hypothesis that sunspots and other related disturbances of the solar atmosphere owe their periodicity to the varying effects of the planets as they approach and recede from the Sun in their eccentric orbits, and as they combine or oppose their effects according to their relative positions. This does not mean that the energy of the solar disturbances is supposed to come from the planets, but merely that their variations act like the turning of a switch to determine when and how violently the internal forces of the Sun shall throw the solar atmosphere into commotion. This hypothesis is by no means new, for in one form or another it has been advocated by Wolfer, Birkeland, E. W. Brown, Schuster, Arctowski, and others. The agency through which the planets influence the solar atmosphere is not yet clear. The suggested agencies are the direct pull of gravitation, the tidal effect of the planets, and an electromagnetic effect. In Earth and Sun, the conclusion is reached when the first two are out of the question. A conclusion which E. W. Brown acquiesces. Unless some unknown cause is appealed to, this leaves an electromagnetic hypothesis as the only one which has a reasonable foundation. Schuster inclines to this view. The conclusions set forth in Earth and Sun as to the electrical nature of the Sun's influence on the Earth point somewhat in the same direction. Hence in this chapter we shall inquire what would happen to the Sun, and hence to the Earth, on their journey through space, if the solar atmosphere is actually subject to disturbance by the electrical or other effects of other heavenly bodies. It need hardly be pointed out that we are here venturing into highly speculative ground, and that the verity or falsity of the conclusions reached in this chapter has nothing to do with the validity of the reasoning in previous chapters. Those chapters are based on the assumption that terrestrial causes of climatic changes are supplemented by solar disturbances which produce their effect, partially through variations in temperature, but also through variations in the intensity and paths of cyclonic storms. The present chapter seeks to shed some light on the possible causes and sequence of solar disturbances. Let us begin by scanning the available evidence as to solar disturbances previous to the time when accurate sunspot records are available. Two rather slender bits of evidence point to cycles of solar activity lasting hundreds of years. One of these has already been discussed in Chapter 6, when the climatic stress of the 14th century was described. At that time, sunspots are known to have been unusually numerous, and there were great climatic extremes. Lakes overflowed in Central Asia, storms, droughts, floods, and cold winters were unusually severe in Europe. The Caspian Sea rose with great rapidity. The trees in California grew with a vigor unknown for centuries. The most terrible of recorded famines occurred in England and India. The Eskimos were probably driven south by increasing snowiness in Greenland, and the Mayas of Yucatan appear to have made their last weak attempt at a revival of civilization under the stimulus of greater storminess and less constant rainfall. The second bit of evidence is found in recent exhaustive studies of periodicities by Turner and other astronomers. They have sought every possible natural occurrence for which a numerical record is available for a long period. The most valuable records appear to be those of tree growth, Nile floods, Chinese earthquakes, and sunspots. Turner reaches the conclusion that all four types of phenomena show the same periodicity, namely cycles with an average length of about 260 to 280 years. He suggests that if this is true, the cycles in tree growth and in floods, both of which are climatic, are probably due to a non-terrestrial cause. The fact that sunspots show similar cycles suggests that the sun's variations are the cause. These two bits of evidence are far too slight to form the foundation of any theory as to changes in solar activity in the geological past. Nevertheless, it may be helpful to set forth certain possibilities as a stimulus to further research. For example, it has been suggested that meteoric bodies may have fallen into the sun and caused it suddenly to flare up, as it were. This is not impossible, although it does not appear to have taken place since men became advanced enough to make careful observations. Moreover, the meteorites which now fall on the Earth are extremely small, the average size being computed as no larger than a grain of wheat. The largest ever found on the Earth's surface, at Bacubirito in Mexico, weighs only about 50 tons, while within the rocks the evidence of meteorites are extremely scanty and insignificant. If meteorites had fallen into the sun often enough, and of sufficient size to cause glacial fluctuations and historic pulsations of climate, it seems highly probable that the Earth would show much more evidence of having been similarly disturbed, and even if the sun should be bombarded by large meteors, the result would probably not be sudden cold periods, which are the most notable phenomena of the Earth's climatic history, but sudden warm periods followed by slow cooling. Nevertheless, the disturbance of the sun by collusion with meteoric matter can by no means be excluded as a possible cause of climatic variations. Allied to the preceding hypothesis is Shapley's nebula hypothesis. At frequent intervals, averaging about once a year during the last 30 years, astronomers have discovered what are known as novae. These are stars which were previously faint or even invisible, but which flash suddenly into brilliancy. Often their light-giving power rises 7 or 8 magnitudes, 1,000-fold. In addition to the spectacular novae, there are numerous irregular variables whose brilliancy changes into every ratio from a few % up to several magnitudes. Most of them are located in the vicinity of nebulae, as is also the case with novae. This, as well as other facts, makes it possible that all these stars are friction variables, as Shapley calls them. Apparently, as they pass through the nebulae, they come into contact with its highly diffused matter and thereby become bright, much as the Earth would become bright if its atmosphere were filled with millions of almost infinitesimally small meteorites. A star may also lose brilliancy if nebulous matter intervenes between it and the observer. If our Sun has been subjected to any of these changes, some sort of climatic effect must have been produced. Interpersonal communication, Shapley amplifies the nebular climatic hypothesis as follows. Within 700 light-years of the Sun in many directions, Taurus, Cygnus, Ophiuchus, Scorpio are great diffuse clouds of nebulosity, some bright, most of them dark. The probability that stars moving in the general region of such clouds will encounter this material is very high, for the clouds fill enormous volumes of space, e.g., probably more than 100,000 cubic light-years in the Orion region, and are presumably composed of rarefied gases or of dust particles. Probably throughout all our part of space, such nebulosity exists. It is all around us, we are sure, but only in certain regions is it dense enough to affect conspicuously the stars involved in it. If a star moving at high velocity should collide with a dense part of such a nebulous cloud, we should probably have a typical nova. If the relative velocity of nebulous material and star were low or moderate, or if the material were rare, we should not expect a conspicuous effect on the star's light. In the nebulous region of Orion, which is probably of unusually high density, there are about 100 known stars, varying between 20% and 80% of their total light, all of them irregularly, some slowly, some suddenly. Apparently they are friction variables. Some of the variables suddenly lose 40% of their light as if blanketed by nebulous matter. In the Trifid Nebula, there are variables like those of Orion, in Messier 8 also, and probably many of the 100 or so around the Rio Ophiuchi region belonging to this kind. I believe that our Sun could not have been a typical nova, at least not since the Archerozoic, that is, for perhaps 1 billion years. I believe we have in geological climates final proof of this, because it increased the amount of solar radiation by 1,000 times, as in a typical nova, would certainly punctuate emphatically the life cycle of the Earth, even if the cause of the nova would not at the same time eliminate the smaller planets. But the Sun may have been one of these miniature novae or friction variables, and I believe it very probable that its wanderings through this part of space could not long leave its mean temperature unaffected to the amount of a few percent. One reason we have not had this proposal insisted upon before is that the data back of it are mostly new. The Orion variables have been only recently discovered and studied. The distribution and content of the dark nebulae are hardly as yet generally known. This interesting hypothesis cannot be hastily dismissed. If the Sun should pass through a nebula, it seems inevitable that there would be at least slight climatic effects, and perhaps catastrophic effects, through the action of the gaseous matter, not only on the Sun but on the Earth's own atmosphere. As an explanation of the general climatic conditions of the past, however, Shapley points out that the hypothesis has the objection of being vague, and that nebulosity should not be regarded as more than a possible factor. One of the chief difficulties seems to be the enormously wide distribution of as yet undiscovered nebulous matter which must be assumed if any large share of the Earth's repeated climatic changes is to be ascribed to such matter. If such matter is actually abundant in space, it is hard to see how any but the nearest stars would be visible. Another objection is that there is no known nebulosity near at hand with which to connect the climatic vicissitudes of the last glacial period. Moreover, the known nebulae are so much less numerous than stars that the chances that the Sun will encounter one of them are extremely slight. This, however, is not an objection, for Shapley points out that during geological times, the Sun can never have varied as much as do the nova, or even as most of the friction variables. Thus the hypothesis stands as one that is worth investigating, but that cannot be finally rejected or accepted until it is made more definite and until more information is available. Another suggested cause of solar variations is a relatively sudden contraction of the Sun, such as that which sometimes occurs on the Earth, when continents are uplifted and mountains upheaved. It seems improbable that this could have occurred in a gaseous body like the Sun, lacking as it does any solid crust which resists a change of form. The Sun probably shrinks steadily, hence any climatic effects thus produced must be extremely gradual and must tend steadily in one direction for millions of years. Still another suggestion is that the tidal action of the stars and other bodies which may chance to approach the Sun's path may cause disturbances of the solar atmosphere. The vast kaleidoscope of space is never quiet. The Sun, the stars, and all the other heavenly bodies are moving, often with enormous speed. Hence the effect of gravitation upon the Sun must vary constantly and irregularly, as befits the geological requirements. In the case of the planets, however, the tidal effect does not seem competent to produce the movements of the solar atmosphere which appear to be concerned in the inception of sunspots. Moreover, there is only the most remote probability that a star and the Sun will approach near enough to one another to produce a pronounced gravitational disturbance in the solar atmosphere. For instance, if it be assumed that changes in Jupiter's tidal effect on the Sun are the main factor in regulating the present difference between sunspot maxima and sunspot minima, the chances that a star or some non-luminous body of solar mass will approach near enough to stimulate solar activity and thereby bring on glaciation are only 1 in 12 billion years, as will be explained below. This seems to make a gravitational hypothesis impossible. Another possible cause of solar disturbances is that the stars in their flight through space may exert an electrical influence which upsets the equilibrium of the solar atmosphere. At first thought, this seems even more impossible than a gravitational effect. Electrostatic effects, however, differ greatly from those of tides. They vary as the diameter of a body instead of as its mass. The differentials are also inversely as the square of the distance instead of as the cube. Electrostatic effects also increase as a fourth power of the temperature, or at least would do so if they followed the law of black bodies. They are stimulated by the approach of one body to another, and they are cumulative, for if ions arrive from space, they must accumulate until the body to which they have come begins to discharge them. Hence, on the basis of assumptions such as those used in the preceding paragraph, the changes of an electrical disturbance of the solar atmosphere sufficient to cause glaciation on the Earth may be as high as 1 in 20 or 30 million years. This seems to put an electrical hypothesis within the bounds of possibility. Further that we cannot now go. There may be other hypotheses which fit the facts much better, but none seems yet to have been suggested. In the rest of this chapter, the tidal and electrical hypothesis of stellar action on the Sun will be taken up in detail. The tidal hypothesis is considered because in discussions of the effect of the planets it has hitherto held almost the entire field. The electrical hypothesis will be considered because it appears to be the best yet suggested, although it still seems doubtful whether electrical effects can be of appreciable importance over such vast distances as are inevitably involved. The discussion of both hypotheses will necessarily be somewhat technical and will appeal to the astronomer more than to the layman. It does not form a necessary part of this book, for it has no bearing on our main thesis of the effect of the Sun on the Earth. It is given here because ultimately the question of changes in solar activity during geological times must be faced. In the astronomical portion of the following discussion, we shall follow Jeans, his admirable attempt at a mathematical analysis of the motion of the universe. Jeans divides the heavenly bodies into 5 main types. 1. Spiral nebulae, which are thought by some astronomers to be systems like our own in the making, and by others to be independent universes lying in vast distances beyond the limits of our galactic universe, as it is called from the galaxy or Milky Way. 2. Nebula of a similar type, called planetary. These lie within the galactic portion of the universe and seem to be early stages of what may someday be stars or solar systems. 3. Binary or multiple stars, which are extraordinarily numerous. In some parts of the heavens they form 50 or even 60% of the stars, and in the galaxy as a whole they seem to form fully 1/3. 4. Star clusters. These consist of about 100 groups of stars, in each of which the stars move together in the same direction with approximately the same velocity. These, like the spiral nebulae, are thought by some astronomers to lie outside the limits of the galaxy, but this is far from certain. 5. The solar system. According to Jeans, this seems to be unique. It does not fit into the general mathematical theory by which he explains spiral nebulae, planetary nebulae, binary stars, and star clusters. It seems to demand a special explanation, such as is furnished by tidal disruption due to the passage of the Sun close to another star. The part of Jeans' work which specially concerns us is his study of the probability that some other star will approach the Sun closely enough to have an appreciable gravitative or electrical effect, and thus cause disturbances in the solar atmosphere. Of course, both the star and the Sun are moving, but to avoid circumlocution, we shall speak of such mutual approaches simply as approaches of the Sun. For our present purpose, the most fundamental fact may be summed up in a quotation from Jeans, in which he says that most stars show evidence of having experienced considerable disturbances by other systems. There is no reason why our solar system should be expected to have escaped the common fate. Jeans gives a careful calculation from which it is possible to derive some idea of the probability of any given degree of approach to the Sun and some other star. Of course, all such calculations must be based on certain assumptions. The assumptions made by Jeans are such as to make the probability of close approaches as great as possible. For example, he allows only 560 million years for the entire evolution of the Sun, whereas some astronomers and geologists would put the figure 10 or more times as high. Nevertheless, Jeans' assumptions, at least, show the order of magnitude which we may expect on the basis of reasonable astronomical conclusions. According to the planetary hypothesis of sunspots, the difference in the effect of Jupiter when it is nearest and farthest from the Sun is the main factor in starting the sunspot cycle and hence the corresponding terrestrial cycle. The climatic difference between sunspot maxima and minima, as measured by temperature, apparently amounts to at least a 20th and perhaps a 10th of the difference between the climate of the last glacial epoch and the present. We may suppose, then, that a body which introduced a gravitative or electrical factor 20 times as great as the difference in Jupiter's effect at its maximum and minimum distances from the Sun would cause a glacial epoch if the effect lasted long enough. Of course, the other planets combine their effects with that of Jupiter, but for the sake of simplicity, it will leave the others out of account. The difference between Jupiter's maximum and minimum tidal effect on the Sun amounts to 29% of the planet's average effect. The corresponding difference, according to the electrical hypothesis, is about 19%. For electrostatic action varies as a square of the distance instead of as the cube. Let us assume that a body exerting 4 times Jupiter's present tidal effect, and placed at the average distance of Jupiter from the Sun, would disturb the Sun's atmosphere 20 times as much as the present difference between sunspot maxima and minima, and thus perhaps cause a glacial period on the Earth. On the basis of this assumption, our first problem is to estimate the frequency with which a star, visible or dark, is likely to approach near enough to the Sun to produce a tidal effect 4 times that of Jupiter. The number of visible stars is known, or at least well established. As to dark stars, which have grown cool, Our Highness believed that they are 100 times as numerous as bright stars. Few astronomers believe that there are less than 3 or 4 times as many. Dr. Shapley of the Harvard Observatory states that a new investigation of the matter suggests that 8 or 10 is probably a maximum figure. Let us assume that 9 is correct. The average visible star, as far as measured, has a mass about twice that of the Sun, or about 2,100 times that of Jupiter. The distances of the stars have been measured in hundreds of cases, and thus we can estimate how many stars, both visible and invisible, are on an average contained in a given volume of space. On this basis, Jeans estimates that there is only one chance in 30 billion years that a visible star will approach within 2.8 times the distance of Neptune from the Sun, that is, within about 8 billion miles. If we include the invisible stars, the chances become 1 in 3 billion years. In order to produce 4 times the tidal effect of Jupiter, however, the average star would have to approach within about 4 billion miles of the Sun, and the chances of that are only 1 in 12 billion years. The disturbing star would be only 40% farther from the Sun than Neptune, and would almost pass within the solar system. Even though Jeans holds that the frequency of the mutual approach of the Sun and a star was probably much greater in the distant past than at present, the figures just given lend little support to the tidal hypothesis. In fact, they apparently throw it out of court. It will be remembered that Jeans has made assumptions which give as high a frequency of stellar encounters as is consistent with the astronomical facts. We have assumed 9 dark stars for every bright one, which may be a liberal estimate. Also, although we have assumed that a disturbance of the Sun's atmosphere sufficient to cause a glacial period would arise from a tidal effect only 20 times as great as the difference in Jupiter's effect when nearest the Sun and farthest away, in our computations, this has actually been reduced to 13. With all these favourable assumptions, the chances of a stellar approach of the sort here described are now only 1 in 12 billion years. Yet within 100 million years, according to many estimates of geological time, and almost certainly within a billion, there have been at least half a dozen glaciations. Our use of Jean's data interposes another and equally insuperable difficulty to any tidal hypothesis. 4 billion miles is a very short distance in the eyes of an astronomer. At that distance, a star twice the size of the Sun would attract the outer planets more strongly than the Sun itself, and might capture them. If a star should come within 4 billion miles of the Sun, its effect in distorting the orbits of all the planets would be great. If this had happened often enough to cause all the glaciations known to geologists, the planetary orbits would be strongly elliptical instead of almost circular. The considerations here advanced militate so strongly against the tidal hypothesis of solar disturbances that it seems scarcely worthwhile to consider it further. Let us turn now to the electrical hypothesis. Here the conditions are fundamentally different from those of the tidal hypothesis. In the first place, the electrostatic effect of a body has nothing to do with its mass, but depends on the area of its surface. That is, it varies as the square of the radius. Second, the emission of electrons varies exponentially. If hot, glowing stars follow the same law as black bodies at lower temperatures, the emission of electrons, like the emission of other kinds of energy, varies at the fourth power of the absolute temperature. In other words, suppose there are two black bodies, otherwise alike, but one with a temperature of 27 degrees Celsius or 300 degrees on the absolute scale, and the other with 600 degrees on the absolute scale. The temperature of one is twice as high as that of the other, but the electrostatic effect will be 16 times as great. Third, the number of electrons that reach a given body varies inversely as the square of the distance, instead of as the cube, which is the case with tide-making forces. In order to use these three principles in calculating the effect of the stars, we must know the diameters, distances, temperature, and number of the stars. The distances and number may safely be taken as given by Jeans in the calculations already cited. As to the diameters, the measurements of the stars thus far made indicate that the average mass is about twice that of the Sun. The average density, as deduced by Shapley from the movements of double stars, is about 1/8 the solar density. This would give an average diameter about 2.5 times that of the Sun. For the dark stars, we shall assume for convenience that they are 10 times as numerous as the bright ones. We shall also assume that their diameter is half that of the Sun, for being cool they must be relatively dense, and that their temperature is the same as that which we shall assume for Jupiter. As to Jupiter, we shall continue our former assumption that a body with 4 times the effectiveness of that planet, which here means with twice as great a radius, would disturb the Sun enough to cause glaciation. It would produce about 20 times the electrostatic effect, which now appears to be associated with the difference in Jupiter's effect at maximum and minimum. The temperature of Jupiter must also be taken into account. The planet is supposed to be hot because its density is low, being only about 1.25 that of water. Nevertheless, it is probably not luminous, for as Moulton puts it, shadows upon it are black, and its moons show no sign of illumination except from the Sun. Hence a temperature of about 600 degrees Celsius, or approximately 900 degrees on the absolute scale, seems to be the highest that can reasonably be assigned to the cold outer layer whence electrons are emitted. As to the temperature of the Sun, we shall adopt the common estimate of about 6,300 degrees Celsius on the absolute scale. The outer stars will be taken as averaging the same, although of course they vary greatly. When Jean's method of calculating the probability of a mutual approach of the Sun and a star is applied to the assumptions given above, the results are as shown in Table 5. On that basis, the dark stars seem to be of negligible importance so far as the electrical hypothesis is concerned. Even though they may be 10 times as numerous as the bright ones, there appears to be only one chance in 130 billion years that one of them will approach the Sun closely enough to cause the assumed disturbance of the solar atmosphere. On the other hand, if all the visible stars were the size of the Sun, and as hot as that body, their electrical effect would be fourfold that of our assumed dark star because of their size, and 2,401 times as great because of their temperature, or approximately 10,000 times as great. Under such conditions, the theoretical chance of an approach, that would cause glaciation is 1 in 130 million years. If the average visible star is somewhat cooler than the Sun and has a radius about 2.5 times as great, as appears to be the fact, the chances rise to 1 in 38 million years. A slight and wholly reasonable change in our assumptions would reduce the last figure to only 5 or 10 million. For instance, the Earth's mean temperature during the glacial period has been assumed as 10 degrees Celsius lower than now, but the difference may have been only 6 degrees. Again, the temperature of the outer atmosphere at Jupiter, where the electrons are shot out, may be only 500 degrees or 700 degrees absolute instead of 900 degrees, or the diameter of the average star may be 5 or 10 times that of the Sun instead of only 2.5 times as great. All this, however, may for the present be disregarded. The essential point is that even when the assumptions err on the side of conservatism, the results are of an order of magnitude which puts the electrical hypothesis within the bounds of possibility. Whereas similar assumptions put the tidal hypothesis, with its single approach in 12 billion years, far beyond those limits. The figures for Betelgeuse in Table 5 are interesting. At a meeting of the American Association for the Advancement of Science in December 1920, Michelson reported that by measurements of the interference of light coming from about 2 sides of that bright star in Orion, the observers at Mount Wilson had confirmed the recent estimates of 3 other authorities that the star's diameter is about 218 million miles, or 250 times that of the Sun. If other stars so much surpass the estimates of only 1 decade or 2 ago, the average diameter of all the visible stars must be many times that of the Sun. The low figure for Betelgeuse in section D of the table means that if all the stars were as large as Betelgeuse, several might often be near enough to cause profound disturbances of the solar atmosphere. Nevertheless, because of the low temperature of the giant red stars of the Betelgeuse type, the distance at which one of them would produce a single electrical effect is only about 5 times the distance at which our assumed average star would produce the same effect. This, to be sure, is on the assumption that the radiation of energy from incandescent bodies varies according to temperature in the same ratio as the radiation from black bodies. Even if this assumption departs somewhat from the truth, it still seems almost certain that the lower temperature of the red compared with the high temperature of the white stars must, to a considerable degree, reduce the difference in electrical effect which would otherwise arise from their size. Table 5 is displayed on the page. Theoretical probability of stellar approaches. There are 5 columns, with categories compared to dark stars, the Sun, average star, and Betelgeuse. Thus far, in our attempt to estimate the distance at which a star might disturb the Sun enough to cause glaciation on the Earth, we have considered only the star's size and temperature. No account has been taken of the degree to which its atmosphere is disturbed. Yet in the case of the Sun, this seems to be one of the most important factors. The magnetic field of sunspots is sometimes 50 or 100 times as strong as that of the Sun in general. The strength of the magnetic field appears to depend on the strength of the electrical currents in the solar atmosphere. But the intensity of the sunspots, and by inference of the electrical currents, may depend on the electrical action of Jupiter and the other planets. If we apply a similar line of reasoning to the stars, we are at once led to question whether the electrical activity of double stars may not be enormously greater than that of isolated stars like the Sun. If this line of reasoning is correct, the atmosphere of every double star must be in a state of commotion vastly greater to that of the Sun's atmosphere, even when it is most disturbed. For example, suppose the Sun were accompanied by a comparison of equal size at a distance of 1 million miles, which would make it much like many known double stars. Suppose also that in accordance with the general laws of physics, the electrical effect of the 2 suns upon one another is proportional to the 4th power of the temperature, the square of the radius, and the inverse square of the distance. Thus the effect of each sun upon the other would be 60 billion 6 by 10 to the power of 10 times as great as the present electrical effect of Jupiter upon the Sun. Just what this would mean as to the net effect of a pair of such suns upon the electrical potential of other bodies at a distance we can only conjecture. The outstanding fact is that the electrical conditions of a double star must be radically different and vastly more intense than those of a single star like the Sun. This conclusion carries weighty consequences. At present, 20 or more stars are known to be located within about 100 trillion miles of the Sun, 5 parsecs, as the astronomers say, or 16.5 light years. According to the assumptions employed in Table 5, an average single star would influence the Sun enough to cause glaciation if it came within approximately 200 billion miles. If the star were double, however, it might have an electrical capacity enormously greater than that of the Sun. Then it would be able to cause glaciation at a correspondingly great distance. Today, Alpha Centauri, the nearest known star about 25 trillion miles or 4.3 light-years from the Sun, and Sirius, the brightest star in the heavens, is about 50 trillion miles away, or 8.5 light-years. If these stars were single and had diameter 3 times that of the Sun, and if they were of the same temperature as has been assumed for Betelgeuse, which is about 50 times as far away as Alpha Centauri, the relative effects of the 3 stars upon the Sun would be, approximately, Betelgeuse 700, Alpha Centauri 250, Sirius 1. But Alpha Centauri is triple and Sirius double, and both are much hotter than Betelgeuse. Hence Alpha Centauri and even Sirius may be far more effective than Betelgeuse. The 2 main components of Alpha Centauri are separated by an average distance of about 2,200,000,000 miles, or somewhat less than that of Neptune from the Sun. A third and far fainter star, one of the faintest yet measured, revolves around them at a great distance. In mass and brightness, the 2 main components are about like the Sun, and we will assume that the same is true of their radius. Then, according to the assumptions made above, their effect in disturbing one another electrically would be about 10,000 times the total effect of Jupiter upon the Sun, or 2,500 times the effect that we have assumed to be necessary to produce a glacial period. We have already seen in Table 5 that, according to our assumptions, a single star like the Sun would have to approach within 120 billion miles of the solar system, or within 2% of a light-year, in order to cause glaciation. By a similar process of reasoning, it appears that if the mutual electrical excitation of the 2 main parts of Alpha Centauri, regardless of the third part, is proportional to the apparent excitation of the Sun by Jupiter, Alpha Centauri would be 5,000 times as effective as the Sun. In other words, if it came within 8,500,000,000,000 miles of the Sun, or 1.4 light-years, it would so change the electrical conditions as to produce a glacial epoch. In that case, Alpha Centauri is now so near that it introduces a disturbing effect equal to about 1/6 of the effect needed to cause glaciation on the Earth. Sirius and perhaps others of the nearer and brighter or lighter stars may also create appreciable disturbances in the electrical condition of the Sun's atmosphere, and may have done so at a much greater degree in the past, or be destined to do so in the future. Thus, an electrical hypothesis of solar disturbances seems to indicate that the position of the Sun in respect to other stars may be a factor of great importance in determining the Earth's climate. End of section 14. Section 15 of Climatic Changes, the Nature and Causes by Ellsworth Huntington. This LibriVox recording is in the public domain, recorded by Leon Harvey. Chapter 15. The Sun's Journey Through Space. Having gained some idea of the nature of the electrical hypothesis of solar disturbances, and of the possible effect of other bodies upon the Sun's atmosphere, let us now compare the astronomical data with those of geology. Let us take up 5 chief points for which the geologist demands an explanation, and which any hypothesis must meet if it is to be permanently accepted. These are 1. The irregular intervals at which glacial periods occur. 2. The division of glacial periods into epochs separated sometimes by hundreds of thousands of years. 3. The length of glacial periods and epochs. 4. The occurrence of glacial status and historic pulsations in the form of small climatic waves superposed upon the larger waves of glacial epochs. 5. The occurrence of climatic conditions much milder than those of today, not only in the middle portion of the great geological eras, but even in some of the recent interglacial epochs. 1. The irregular duration of the interval from one glacial epoch to another corresponds with the irregular distribution of the stars. If glaciation is indirectly due to stellar influences, the epochs might fall close together, or might be far apart. If the average interval were 10 million years, one interval might be 30 million or more, and the next only 1 or 200,000. According to Schuchert, the known periods of glacial or semi-glacial climate have been approximately as follows. List of glacial periods. 1. Archaeozoic. 1/4 of geological time, or perhaps much more. No known glacial periods. 2. Proterozoic. 1/4 of geological time. A. Oldest known glacial period near base of Proterozoic in Canada. Evidence widely distributed. B. Indian glacial period. Time unknown. C. African glacial period. Time unknown. D. Glaciation near end of Proterozoic in Australia, Norway, and China. 3. Paleozoic. 1/4 of geological time. A. Late Ordovician. Local in Arctic Norway. B. Silurian. Local in Alaska. C. Early Devonian. Local in South Africa. D. Early Permian. Worldwide and very severe. 4. Mesozoic and Cenozoic. 1/4 of geological time. A. B. None definitely determined during Mesozoic, although there appears to have been periods of cooling. A. In the late Triassic and B. in the late Cretacic, with at least local glaciation in early Eocene. C. Severe glacial period during Pleistocene. This table suggests an interesting inquiry. During the last few decades, there has been great interest in ancient glaciation, and geologists have carefully examined rocks of all ages for signs of glacial deposits. In spite of the large parts of the Earth which are covered with deposits belonging to the Mesozoic and Cenozoic, which form the last quarter of geological time, the only signs of actual glaciation are those of the Great Pleistocene period and a few local occurrences at the end of the Mesozoic or beginning of the Cenozoic. Late in the Triassic and early in the Jurassic, the climate appears to have been rigorous, although no tillites have been found to demonstrate glaciation. In the preceding quarter, that is, the Paleozoic, the Permian glaciation was more severe than that of the Pleistocene, and the Devonian than that of the Eocene, while the Ordovician evidences of low temperature are stronger than those at the end of the Triassic. In view of the fact that rocks of Paleozoic age cover much smaller areas than do those of later age, the 3 Paleozoic glaciations seem to indicate a relative frequency of glaciation. Going back to the Proterozoic, it is astonishing to find that evidence of 2 highly developed glacial periods, and possibly 4, has been discovered. Since the Indian and the African glaciations of Proterozoic times are as yet undated, we cannot be sure that they are not of the same date as the others. Nevertheless, even 2 is a surprising number, for not only are most Proterozoic rocks so metamorphosed that possible evidences of glacial origin are destroyed, but rocks of that age occupy far smaller areas than either those of Paleozoic or, still more, Mesozoic and Cenozoic age. Thus the record of the last 3 quarters of geological time suggests that if rocks of all ages were as abundant and as easily studied as those of the latter periods, the frequency of glacial periods would be found to increase as one goes backward toward the beginnings of the Earth's history. This is interesting, for Jeans holds that the chances that the stars would approach one another were probably greater in the past than at present. The conclusion is based on the assumption that our universe is like the spiral nebulae in which the orbits of the various members are nearly circular during their younger stages. Jeans considers it certain that in such cases the orbits will gradually become larger and more elliptical because of the attraction of one body for another. Thus, as time goes on, the stars will be more widely distributed and the chances of approach will diminish. If this is correct, the agreement between astronomical theory and geological conclusion suggests that the two are at least not in opposition. The first quarter of geological time, as well as the last 3, must be considered in this connection. During the Archaeozoic, no evidence of glaciation has yet been discovered. This suggests that the geological facts disprove the astronomical theory, but our knowledge of early geological times is extremely limited, so limited that lack of evidence of glaciation in the Archaeozoic may have no significance. Archaeozoic rocks have been studied minutely over a very small percentage of the Earth's land surface. Moreover, they are highly metamorphosed, so that even if glacial tills existed, it would be hard to recognize them. Third, according to both the nebular and the planetesimal hypothesis, it seems possible that during the earliest stages of geological history, the Earth's interior was somewhat warmer than now, and the surface may have been warmed more than at present by conduction, by lava flows, and by the fall of meteorites. If the Earth during the Archaeozoic period emitted enough heat to raise its surface temperature a few degrees, the heat would not prevent the development of low forms of life, but might effectively prevent all glaciation. This does not mean that it would prevent changes of climate, but merely changes so extreme that their record would be preserved by means of ice. It will be most interesting to see whether future investigations in geology and astronomy indicate either a semi-uniform distribution of glacial periods throughout the past, or a more or less regular decrease in frequency from early times down to the present. 2. The Pleistocene glacial period was divided into at least 4 epochs, while in the Permian at least one interglacial epoch seems certain, and in some places the alternation between glacial and non-glacial beds suggests no less than 9. In the other glaciations, the evidence is not yet clear. The question of periodicity is so important that it overthrows most glacial hypotheses. Indeed, had their authors known the facts as established in recent years, most of the hypotheses would never have been advanced. The carbon dioxide hypothesis is the only one which was framed with geologically rapid climatic alterations in mind. It certainly explains the facts of periodicity better than does any of its predecessors, but even so it does not account for the intimate way in which variations of all degrees, from those of the weather up to glacial epochs, seem to grade into one another. According to our stellar hypothesis, occasional groups of glacial epochs would be expected to occur close together and to form long glacial periods. This is because many of the stars belong to groups or clusters in which the stars move in parallel paths. A good example is the cluster in the Hyades, where Boss has studied 39 stars with special care. The stars are grouped about a center about 130 light-years from the Sun. The stars themselves are scattered over an area about 30 light-years in diameter. They average about the same distance apart as do those near the Sun, but toward the center of the group they are somewhat closer together. The whole 39 sweep forward in essentially parallel paths. Boss estimates that 800,000 years ago the cluster was only half as far from the Sun as the present, but probably that was as near as it had been during recent geological times. All of the 39 stars of this cluster, as Moulton puts it, are much greater in light-giving power than the Sun. The luminosities of even the 5 smallest are from 5 to 10 times that of the Sun, while the largest are 100 times greater in light-giving power than our own luminary. Their masses are probably much greater than that of the Sun. If the Sun were to pass through such a cluster, first one star and then another might come so near as to cause a profound disturbance in the Sun's atmosphere. 3. Another important point upon which a glacial hypothesis may come to grief is the length of the periods, or rather of the epochs, which compose the periods. During the last or Pleistocene glacial period, the evidence in America and Europe indicates that the interglacial epochs varied in length and that the latter ones were shorter than the earlier. Chamberlain and Salisbury, from a comparison of various authorities, estimate that the intervals from one glacial epoch to another form a declining series, which may be roughly expressed as follows: 16.8421, where unity is the interval from the climax of the late Wisconsin or last glacial epoch to the present. Most authorities estimate the culmination of the late Wisconsin glaciation as 20 or 30,000 years ago. Penck estimates the length of the last interglacial period as 60,000 years, and the preceding one as 240,000. R.T. Chamberlain, as already stated, finds that the consensus of opinion is that interglacial epochs have averaged 5 times as long as the glacial epochs. The actual duration of the various glaciations probably did not vary in so great a ratio as did the intervals for one glaciation to another. The main point, however, is the irregularity of the various periods. The relation of the stellar electrical hypothesis to the length of glacial epochs may be estimated from column C in Table 5. There we see that the distances at which a star might possibly disturb the Sun enough to cause glaciation range all the way from 120 billion miles in the case of a small star like the Sun to 3,200 billion in the case of Betelgeuse, while for double stars the figure may rise 100 times higher. From this we can calculate how long it would take a star to pass from a point where its influence would first amount to a quarter of the assumed maximum to a similar point on the other side of the Sun. In making these calculations, we will assume that the relative rate at which the star and the Sun approach each other is about 22 miles per second, or 700 million miles per year, which is the average rate of motion of all the known stars. According to the distance in Table 5, this gives a range from about 500 years up to about 10,000, which might rise from 1 million in the case of double stars. Of course, the time might be relatively short in the Sun and a rapidly moving star were approaching one another almost directly, or extremely long if the Sun and the star were moving in almost the same direction and at somewhat similar rates. A condition more common than the other, here, as in so many other cases, the essential point is that the figures which we thus obtain seem to be of the right order of magnitude. 4. Post-glacial climatic stages are so well known that in Europe they have definite names. Their sequence has already been discussed in Chapter 12. Fossils found in the great peat bogs of Denmark and Scandinavia, for example, prove that since the final disappearance of the continental ice cap at the close of Wisconsin, there has been at least one period where the climate of Europe was distinctly milder than now. Directly overlying the sheets of glacial drift laid down by the ice, there is a flora corresponding to that of the present tundras. Next come remains of a forest vegetation dominated by birches and poplars, showing that the climate was growing a little warmer. Third, there follow evidences of a still more favourable climate in the form of a forest dominated by pines. Fourth, one where oak predominates. And fifth, a flora similar to that of the Black Forest in Germany, indicating that in Scandinavia the temperature was then decidedly higher than today. This fifth flora has retreated southward once more, having been driven back to its present latitude by a slight recurrence of a cool, stormy climate. In Central Asia, evidence of post-glacial stages is found not only in 5 distinct moraines, but in a corresponding series of elevated strands surrounding salt lakes and of river terraces in non-glaciated arid regions. In historic as well as prehistoric times, as we have already seen, there have been climatic fluctuations. For instance, the 12th or 13th century BC appears to have been almost as mild as now, as does the 7th century BC. On the other hand, about 1000 BC, at the time of Christ, and the 14th century, there were times of relative severity. Thus it appears that both on a large and on a small scale, pulsations of climate are the rule. Any hypothesis of climatic changes must satisfy the periods of these pulsations. These conditions furnish a problem which makes it difficult for almost all hypotheses of climatic change. According to the present hypothesis, Earth movements such as are discussed in Chapter 12 may cooperate with 2 astronomical factors. One is the constant change in the positions of the stars, a change which we have already called kaleidoscopic, and the other is the fact that a large proportion of the stars are double or multiple. When one star in a group approaches the Sun closely enough to cause a great solar disturbance, numerous others may approach or recede and have a minor effect. Thus, whenever the Sun is near groups of stars, we should expect that the Earth would show many minor climatic pulsations and stages which might or might not be connected with glaciation. The historic pulsations shown in the curve of tree growth in California, Figure 4, are the sort of changes that would be expected if movements of the stars have an effect on the solar atmosphere. Not only are fully a third of all the visible stars double, as we have already seen, but at least a tenth of these are known to be triple or multiple. In many of the double stars, the 2 bodies are close together and revolve so rapidly that whatever periodicity they might create in the Sun's atmosphere would be very short. In the triplets, however, the third star is ordinarily at least 10 times as far from the other 2 as they are from each other, and its period of rotation sometimes runs into hundreds or thousands of years. An actual multiple star in the constellation Polaris will serve as an example. The main star is believed by genes to consist of 2 parts which are almost in contact and whirl around each other with extraordinary speed in 4 days. If this is true, they must keep each other's atmospheres in a state of intense commotion. Much farther away, a third star revolves around this pair in 12 years. At a much greater distance, a fourth star revolves around the common centre of gravity of itself, and the other 3 in a period which may be 20,000 years. Still more complicated cases probably exist. Suppose such a system were to traverse a path where it would exert a perceptible influence on the Sun for 30 or 40,000 years. The varying movements of its members would produce an intricate series of cycles which might show all sorts of major and minor variations in length and intensity. Thus the varied and irregular stages of glaciation and the pulsations of historic times might be accounted for on the hypothesis of the proximity of the Sun to a multiple star, as well as on that of the less pronounced approach and recession of a number of stars. In addition to all this, an almost infinitely complex series of climatic changes of long and short duration might arise if the Sun passed through a nebula. 5. We have seen in Chapter 8 that the contrast between the somewhat severe climate of the present and the generally mild climate of the past is one of the great geological problems. The glacial period is not a thing of the distant past. Geologists generally recognize that it is still with us. Greenland and Antarctica are both shrouded in ice sheets in latitudes where fossil floras prove that at other periods the climate was as mild as in England or even New Zealand. The present glaciated regions, be it noted, are on the polar borders of the world's two most stormy oceanic areas, just where ice would be expected to last longest according to the solar cyclonic hypothesis. In contrast to the semi-glacial conditions of the present, the last interglacial epoch was so mild that not only men but elephants and hippopotamuses flourished in Central Europe, while at earlier times in the middle of long eras such as the Paleozoic and Mesozoic, corals, cycads and tree ferns flourished within the Arctic Circle. If the electrostellar hypothesis of solar disturbances proves well-founded, it may explain these peculiarities. Periods of mild climate would represent a return of the Sun and the Earth to their normal conditions of quiet. At such times, the atmosphere of the Sun is assumed to be little disturbed by sunspots, faculae, prominences, and other allied evidences of movements, and the rice-grain structure is perhaps the most prominent of the solar markings. The Earth at such times is supposed to be correspondingly free from cyclonic storms. Its winds are then largely of the purely planetary type, such as trade winds and westerlies. Its rainfall also is largely planetary rather than cyclonic. It falls in places such as the heat equator, where the air rises under the influence of heat, or on the windward slopes of mountains, or in regions where warm winds blow from the ocean over cold lands. According to the electrostellar hypothesis, the conditions which prevailed during hundreds of millions of years of mild climate mean merely that the solar system was in parts of the heavens where stars, especially double stars, were rare or small, and electrical disturbances correspondingly weak. Today, on the other hand, the Sun is fairly near a number of stars, many of which are large doubles. Hence it is supposed to be disturbed, although not so much as the height of the last glacial epoch. After the preceding parts of this book had been written, the assistants of Dr. Schlesinger made it possible to test the electrostellar hypothesis by comparing actual astronomical dates with the dates of climatic or solar phenomena. In order to make this possible, Dr. Schlesinger and his assistants have prepared Table 6, giving the position, magnitude, and motions of the 38 nearest stars, and especially the date at which each was nearest the Sun. In column 10, where the dates are given, a minus sign indicates the past and a plus sign the future. Dr. Shapley has kindly added column 12, giving the absolute magnitudes of the stars, that of the Sun being 4.8, and column 13, showing their luminosity or absolute rotation, that of the Sun being unity. Finally, column 14 shows the effective radiation received by the Sun from each star when the star is at a minimum distance. Unity in this case is the effect of a star like the Sun at a distance of 1 light year. It is well known that radiation of all kinds, including light, heat, and electrical emissions, varies in direct proportion to the exposed surface, that is, as the square of the radius of a sphere, and inversely as the square of the distance. From black bodies, as we have seen, the total radiation varies as the fourth power of the absolute temperature. It is not certain that either light or electrical emissions from incandescent bodies vary in quite the same proportion, nor is it yet certain whether luminous or electrical emissions vary exactly together. Nevertheless, they are closely related. Since the light coming from each star is accurately measured, while no information is available as to electrical emissions, we have followed Dr. Shapley's suggestion and used the luminosity of the stars as the best available measure of total radiation. This is presumably an approximate measure of electrical activity, provided some allowance be made for disturbances by outside bodies such as companion stars. Hence the inclusion of column 14. Table 6 is displayed on the page. 38 stars having largest known parallaxes. On the basis of column 14, and of the movements and distances of the stars as given in the other columns, figure 10 has been prepared. This gives an estimate of the approximate electrical energy received by the Sun from the nearest stars for 70,000 years before and after the present. It is based on 26 stars for which complete data are available in Table 6. The inclusion of the other 12 would not alter the form of the curve, for even the largest of them would not carry any part by more than about half of 1%, if as much. Nor would the curve be visibly altered by the emission of all except 4 of the 26 stars actually used. The 4 that are important, and their relative luminosity when nearest the Sun, are Sirius, 429,000, Altair, 153,000, Alpha Centauri, 117,500, and Procyon, 51,300. The figure for the next star is only 4,970, while for this star combined with the other 21 that are unimportant, it is only 24,850. Figure 10 is not carried more than 70,000 years into the past or into the future, because the stars near the Sun at more remote times are not included among the 38 having the largest known parallaxes. That is, they have either moved away or not yet near enough to be included. Indeed, as Dr. Schlesinger strongly emphasizes, there may be swiftly moving, bright or gigantic stars which are now quite far away, but whose inclusion would alter Figure 10 even within the limits of the 140,000 years there shown. It is almost certain, however, that the most that these would do would be to raise, not to obliterate, the minima on either side of the main maximum. In preparing Figure 10, it has been necessary to make allowance for double stars. Passing by the 22 unimportant stars, it appears that the companion of Sirius is 8 or 10 magnitudes smaller than that star, while the companions of Procyon and Altair are 5 or more magnitudes smaller than their bright comrades. This means that the luminosity of the faint components is at most only 1% of that of their brighter companions, and in the case of Sirius, not 1/100th of 1%. Hence their inclusion would have no visible effect on Figure 10. In Alpha Centauri, on the other hand, the two components are of almost the same magnitude. For this reason, the effective radiation of that star, as given in column 14, is doubled in Figure 10, while for another reason it is raised still more. The other reason is that if our inferences as to the electrical effect of the Sun on the Earth and of the planets on the Sun are correct, double stars, as we have seen, must be much more effective electrically than single stars. By the same reasoning, two bright stars close together must excite one another much more than a bright star and a very faint one, even if the distances in both cases are the same. So too, other things being equal, a triple star must be more excited electrically than a double star. Hence, in preparing Figure 10, all double stars receive double weight, and each part of Alpha Centauri receives an additional 50%, because both parts are bright, and because they have a third companion to help in exciting them. Figure 10 is displayed on the page. Climatic changes of 140,000 years as inferred from the stars. According to the electrostellar hypothesis, Alpha Centauri is more important climatically than any other star in the heavens, not only because it is triple and bright, but because it is the nearest of all stars, and moves fairly rapidly. Sirius and Procyon move slowly in respect to the Sun, only about 11 and 8 kilometers per second respectively, and their distances at minimum are fairly large, that is 8 and 10.2 light years. Hence their effect on the Sun changes slowly. Altair moves faster, about 26 kilometers per second, and its minimum distance is 6.4 light years, so that its effect changes fairly rapidly. Alpha Centauri moves about 24 kilometers per second, and its minimum distance is only 3.2 light years, hence its effect changes very rapidly. The change in its apparent luminosity, as seen from the Sun, amounting at maximum to about 30% in 10,000 years against 14% for Altair, 4 for Sirius, and 2 for Procyon. The vast majority of the stars change so much more slowly than even Procyon, that their effect is almost uniform. All the stars at a distance of more than perhaps 20 or 30 light years may be regarded as sending to the Sun a practically unchanging amount of radiation. It is the bright stars within this limit which are important, and their importance increases with their proximity, their speed of motion, and the brightness and number of their companions. Hence Alpha Centauri causes the main maximum in Figure 10, while Sirius, Altair, and Procyon combine to cause a general rise of the curve from the past to the future. Let us now interpret Figure 10 geologically. The low position of the curve 50 to 70,000 years ago suggests a mild interglacial climate distinctly less severe than that of the present. Geologists say that such was the case. The curve suggests a glacial epoch culminating about 28,000 years ago. The best authorities put the climax of the last glacial epoch between 25 and 30,000 years ago. The curve shows amelioration of climate since that time, although it suggests that there is still considerable severity. The retreat of the ice from North America and Europe, and its persistence in Greenland and Antarctica agree with this. And the curve indicates that the change of climate is still persisting, a conclusion in harmony with the evidence as to historic changes. If Alpha Centauri is really so important, the effect of its variations, provided it has any, ought perhaps to be evident in the Sun. The activity of the star's atmosphere presumably varies, for the orbits of the two components have an eccentricity of 0.51. Hence, during their period of revolution, 81.2 years, the distance between them ranges from 1,100,000,000 to 3,300,000,000 miles. They were at a minimum distance in 1388, 1459, 1550, 1631 and 1731, 1794, 1875, and will be again in 1956. In Figure 11 showing sunspot variations, it is noticeable that the years 1794 and 1875 come just at the ends of periods of unusual solar activity, as indicated by the heavy horizontal line. A similar period of great activity seems to have begun about 1914. If its duration equals the average of its two predecessors, it will end about 1950. Back in the 14th century, a period of excessive solar activity, which has already been described, culminated from 1370 to 1385, or just before the two parts of Alpha Centauri were at a minimum distance. Thus, in 3 and perhaps 4 cases, the Sun has been unusually active during a time when the two parts of the star were most rapidly approaching each other, and when their atmospheres were presumably most disturbed and their electrical emanations strongest. The fact that Alpha Centauri, the star which would be expected most strongly to influence the Sun and hence the Earth, was nearest the Sun at the climax of the last glacial epoch, and that today the solar atmosphere is most active when the Sun is presumably most disturbed, may be of no significance. It is given for what it is worth. Its importance lies not in the fact that it proves anything, but that no contradiction is found when we test the electrostellar hypothesis by facts which were not thought of when the hypothesis was framed. A vast amount of astronomical work is still needed before the matter can be brought to any definite conclusion. In case the hypothesis stands firm, it may be possible to use the stars as a help in determining the exact chronology of the later part of geological times. If the hypothesis is disproved, it will merely leave the question of solar variations where it is today. It will not influence the main conclusions of this book as to the causes and nature of climatic changes. Its value lies in the fact that it calls attention to new lines of research. Figure 11 is displayed on the page, sunspot curve showing cycles 1750 to 1920. End of section 15. Section 16 of Climatic Changes, Their Nature and Causes by Ellsworth Huntington. This LibriVox recording is in the public domain. Recorded by Leon Harvey. Chapter 16. The Earth's Crust and the Sun. Although the problems of this book may lead far afield, they ultimately bring us back to the Earth and to the present. Several times in the preceding pages there has been mention of the fact that periods of extreme climatic fluctuations are closely associated with great movements of the Earth's crust, whereby mountains are uplifted and continents upheaved. In attempting to explain this association, the general tendency has been to look largely at the past instead of at the present. Hence it has been almost impossible to choose among 3 possibilities, all beset with difficulties. First, the movements of the crust may have caused the climatic fluctuations. Second, climatic changes may cause crustal movements. And third, variations in solar activity or in some other outside agency may give rise to both types of terrestrial phenomena. The idea that movements of the Earth's crust are the main cause of geological changes of climate is becoming increasingly untenable as the complexity and rapidity of climatic changes become more clear, especially during post-glacial times. It implies that the Earth's surface moves up and down with a speed and facility which appear to be out of the question. If volcanic activity be invoked, the problem becomes no clearer. Even if volcanic dust should fill the air frequently and completely, neither its presence nor absence would produce such peculiar features as the localization of glaciers, the distribution of Lewis, and the mild climate of most parts of geological time. Nevertheless, because of the great difficulties presented by the other two possibilities, many geologists still hold that, directly or indirectly, the greater climatic changes have been mainly due to movements of the Earth's crust and to the reaction of the crustal movements of the atmosphere. The possibility that climatic changes are in themselves a cause of movements of the Earth's crust seems so improbable that no one appears to have investigated with any seriousness. Nevertheless, it is worthwhile to raise the question whether climatic extremes may cooperate with other agencies in setting a time when the Earth's crust shall be deformed. As to the third possibility, it is perfectly logical to ascribe both climatic changes and crustal deformation to some outside agency, solar or otherwise. But hitherto there has been so little evidence on this point that such an ascription has merely begged the question. If heavenly bodies should approach the Earth closely enough so that their gravitational stresses cause crustal deformation, all life would presumably be destroyed. As to the Sun, there has hitherto been no conclusive evidence that is related to crustal movements, although various writers have made suggestions along this line. In this chapter we shall carry these suggestions further, and shall see that they are at least worthy of study. As a preliminary to this study, it may be well to note that the coincidence between movements of the Earth's crust and climatic changes is not so absolute as is sometimes supposed. For example, the profound crustal changes at the end of the Mesozoic were not accompanied by widespread glaciation, so far as is yet known, although the temperature appears to have been lowered. Nor was the violent volcanic and diastrophic activity in the Miocene associated with extreme climates. Indeed, there appears to have been little contrast from zone to zone, for figs, breadfruit trees, tree ferns, and other plants of low latitudes grew in Greenland. Nevertheless, both at the end of the Mesozoic and in the Miocene, the climate may possibly have been severe for a time, although the record is lost. On the other hand, Kirk's recent discovery of glacial till in Alaska between beds carrying an undoubted Middle Silurian fauna indicates glaciation at a time when there was little movement of the crust so far as yet appears. Thus we conclude that while climatic changes and crustal movements usually occur together, they may occur separately. According to the solar cyclonic hypothesis, such a conclusion is to be expected. If the Sun were especially active when the terrestrial conditions prohibited glaciation, changes of climate would still occur, but they would be milder than under other circumstances and would leave little record in the rocks. Or there might be glaciation in high latitudes, such as that of southern Alaska in the Middle Silurian, and none elsewhere. On the other hand, when the Sun was so inactive that no great storminess occurred, the upheaval of continents and the building of mountains might go on without the formation of ice sheets, as apparently happened at the end of the Mesozoic. The lack of absolute coincidence between glaciation and periods of widespread emergence of the lands is evident even today, for there is no reason to suppose that the lands are notably lower or less extensive now than they were during the Pleistocene glaciation. In fact, there is much evidence that many areas have risen since that time. Yet glaciation is now far less extensive than in the Pleistocene. Any attempt to explain this difference on the basis of terrestrial changes is extremely difficult, for the shape and altitude of continents and mountains have not changed much in 20 or 30,000 years. Yet the present moderately mild epoch, like the puzzling interglacial epochs of earlier times, is easily explicable on the assumption that the Sun's atmosphere may sometimes vary in harmony with crustal activity, but does not necessarily do so at all times. Turning now to the main problem of how climatic changes may be connected with movements of the Earth's crust, let us follow our usual method and examine what is happening today. Let us first inquire whether earthquakes, which are one of the chief evidences that crustal movements are actually taking place in our own times, show any connection with sunspots. In order to test this, we have compared Milne's catalogue of destructive earthquakes from 1800 to 1899 with Wolf's sunspot numbers for the same period month by month. The earthquake catalogue, as its compiler describes it, is an attempt to give a list of earthquakes which have announced changes of geological importance in the Earth's crust, movements which have probably resulted in the creation or the extension of a line of fault, the vibrations accompanying which could, with proper instruments, have been recorded over a continent or the whole surface of our world. Small earthquakes have been excluded, while the number of large earthquakes, both for ancient and modern times, has been extended. As an illustration of exclusion, I may mention that between 1800 and 1808, which are years taken at random, I find in Mount's catalogue 407 entries. Only 37 of these, which were accompanied by structural damage, have been retained. Other catalogues, such as those of Perry and Fuchs, have been treated similarly. If the earthquakes in such a carefully selected list bear a distinct relation to sunspots, it is at least possible and perhaps probable that a similar relation may exist between solar activity and geological changes in the Earth's crust. The result of the comparison of earthquakes and sunspots is shown in Table 7. The first column gives the sunspot numbers, the second the number of months that had their respective spot numbers during the century from 1800 to 1899. Column C shows the total number of earthquakes during the months having any particular degree of spottedness, while D, which is the significant column, gives the average number of destructive earthquakes per month under each of the 6 conditions of solar spottedness. Table 7 is displayed on the page. The regularity of column D is so great as to make it almost certain that we are here dealing with a real relationship. Column F, which shows the average number of earthquakes in the months succeeding any given condition of the sun, is still more regular except for the last entry. The chance that 6 numbers taken at random will average themselves in any given order is 1 in 720. In other words, there is 1 chance in 720 that the regularity of column D is accidental, but a column F is as regular as column D except for the last entry. If columns D and E were independent, there would be 1 chance in about 500,000 that the 6 numbers in both columns would fall in the same order, and 1 chance in 14,400 that 5 numbers in each would fall in the same order. But the 2 columns are somewhat related, for although the aftershocks of a great earthquake are never included in Milne's table, a world-shaking earthquake in one region during a given month probably creates conditions that favor similar earthquakes elsewhere during the next month. Hence the probability that we are dealing with a purely accidental arrangement in Table 7 is less than 1 in 14,400 and greater than 1 in 500,000. It may be 1 in 20,000 or 100,000. In any event, it is so slight that there is high probability that directly or indirectly sunspots and earthquakes are somehow connected. In ascertaining the relation between sunspots and earthquakes, it would be well if we could employ the strict method of correlation coefficients. This, however, is impossible for the entire century, for the record is by no means homogeneous. The earlier decades are represented by only about 1/4 as many earthquakes as the latter ones, a condition which is presumably due to lack of information. This makes no difference with the method employed in Table 7, since years with many and few sunspots are distributed almost equally throughout the entire 19th century, but renders this method of correlation and coefficients inapplicable. During the period from 1850 onward, the record is much more nearly homogeneous, though not completely so. Even in these latter decades, however, allowance must be made for the fact that there are more earthquakes in winter than in summer, the average number per month for the 50 years being as follows: January 2.8, February 2.4, March 2.5, April 2.4, May 2.4, June 2.3, July 2.4, August 2.4, September 2.5, October 2.6, November 2.7, December 2.8. The correlation coefficients between the departures from these monthly averages and the corresponding departures from the monthly averages of the sunspots for the same period, 1850 to 1899, are as follows. Sunspots and earthquakes of the same month, positive 0.042 or 1.5 times the probable error. Sunspots of a given month and earthquakes of that month and the next, positive 0.084 or 3.1 times the probable error. Sunspots of 3 consecutive months and earthquakes of 3 consecutive months, allowing a lag of 1 month, i.e. sunspots of January, February, and March compared with earthquakes of February, March, and April. Sunspots of February, March, and April with earthquakes in March, April, and May, etc. Positive 0.112 or 4.1 times the probable error. These coefficients are all small, but the numbers of individual cases, 600 months, is so large that the probable error is greatly reduced, being only standard deviation 0.027 or standard deviation 0.028. Moreover, the nature of our data is such that even if there is a strong connection between solid changes and Earth movements, we should not expect a large correlation coefficient. In the first place, as already mentioned, the earthquake data are not strictly homogeneous. Second, an average of about 2.5 strong earthquakes per month is at best only a most imperfect indication of the actual movement of the Earth's crust. Third, the sunspots are only a partial and imperfect measure of the activity of the Sun's atmosphere. Fourth, the relation between solar activity and earthquakes is almost certainly indirect. In view of all these conditions, the regularity of Table 7 and the fact that the most important correlation coefficient rises are more than 4 times the probable error makes it almost certain that the solar and terrestrial phenomena are really connected. We are now confronted by the perplexing question of how this connection could take place. Thus far, only 3 possibilities present themselves, and each is open to objections. The chief agencies concerned in these 3 possibilities are heat, electricity, and atmospheric pressure. Heat may be dismissed very briefly. We have seen that the Earth's surface becomes relatively cool when the Sun is active. Theoretically, even the slightest change in the temperature of the Earth's surface must influence the thermal gradient far into the interior and hence cause a change of volume which might cause movements of the crust. Practically, the heat of the surface ceases to be of appreciable importance at a depth of perhaps 20 feet, and even at that depth it does not act quickly enough to cause the relatively prompt response which seems to be characteristic of earthquakes in respect to the Sun. The second possibility is based on the relationship between solar and terrestrial electricity. When the Sun is active, the Earth's atmospheric electrical potential is subject to slight variations. It is well known that when 2 opposing points of an ionized solution are oppositely charged electrically, a current passes through the liquid and sets up electrolysis, whereby there is a segregation of materials and a consequent change in the volume of the parts near the respective electrical poles. The same process takes place, although less freely, in a hot mass such as forms the interior of the Earth. The question arises whether internal electrical currents may not pass between the 2 oppositely charged poles of the Earth, or even between the great continental masses and the regions of heavier rock which underlie the oceans. Could this lead to electrolysis, hence to differentiation of volume, and thus to movements of the Earth's crust? Could the results vary in harmony with the Sun? Bowie has shown that numerous measurements of the strength and direction of the Earth's gravitative pull are explicable only on the assumption that the upheaval of a continent or a mountain range is due in part not merely to pressure or even to fluid to the rocks beneath the crust, but also to an actual change in volume whereby the rocks beneath the continent attain relatively great volume and those under the oceans a small volume in proportion to their weight. The query arises whether this change of volume may be related to electrical currents at some depth below the Earth's surface. The objections to this hypothesis are numerous. First, there is little evidence of electrolytic differentiation in the rocks. Second, the outer part of the Earth's crust is a very poor conductor, so that it is doubtful whether even a high degree of electrification of the surface would have much effect on the interior. Third, electrolysis due to any such mild causes as we have here postulated must be an extremely slow process, too slow, presumably, to have any appreciable result within a month or 2. Other objections join with these 3 in making it seem improbable that the Sun's electrical activity has any direct effect upon movements of the Earth's crust. The third or meteorological hypothesis, which makes barometric pressure the main intermediary between solar activity and earthquakes, seems at first sight almost as improbable as the thermal and electrical hypothesis. Nevertheless, it has a certain degree of observational support of a kind which is wholly lacking in the other 2 cases. Among the extensive writings on the periodicity of earthquakes, the one main fact stands out with great distinctness. Earthquakes vary in number according to the season. This fact has already been shown incidentally in the table of earthquake frequency by months. If allowance is made for the fact that February is a short month, there is a regular decrease in the frequency of severe earthquakes from December and January to June. Since most of Milne's earthquakes occur in the northern hemisphere, this means that severe earthquakes occur in winter about 20% oftener than in summer. Table 8 is displayed on the page. The most thorough investigation of this subject seems to have been that of Davison. His results have been worked over and amplified by Knott, who has tested them by Schuster's exact mathematical methods. His results are given in Table 8. Here the northern hemisphere is placed first, then comes the East Indies and the Malay archipelago lying close to the equator, and finally the southern hemisphere. In the Northern Hemisphere, practically all the maxima come in the winter. For the month of December appears in 15 cases out of 25 in column D, while January, February, or November appear in 6 others. It is also noticeable that in 16 cases out of 25, the ratio of the actual to the expected amplitude in column G is 4 or more, so that a real relationship is indicated, while the ratio falls below 3 only in Japan and Zante. The equatorial data, unlike those in the Northern Hemisphere, are indefinite. For in the East Indies, no month shows a marked maximum and the expected amplitude exceeds the actual amplitude. Even in the Malay archipelago, which shows a maximum in May, the ratio of actual to expected amplitude is only 2.6. Turning to the Southern Hemisphere, the winter months of that hemisphere are as strongly marked by a maximum as are the winter months of the Northern Hemisphere. July or August appears in 5 out of 6 cases. Here the ratio between the actual and expected amplitudes is not so great as in the Northern Hemisphere. Nevertheless, it is practically 4 in Chile and exceeds 5 in Peru and Bolivia, and in the data for the entire Southern Hemisphere. The whole relationship between earthquakes and the seasons in the Northern and Southern Hemispheres is summed up in Figure 12, taken from Knott. The Northern Hemisphere shows a regular diminution in earthquake frequency from December until June, and an increase in the rest of the year. In the Southern Hemisphere, the course of events is the same so far as summer and winter are concerned, for August with its maximum comes in winter, while February with its minimum comes in summer. In the Southern Hemisphere, the winter month of greatest seismic activity has over 100% more earthquakes than the summer month of least activity. In the Northern Hemisphere, this difference is about 80%, but this smaller figure occurs partially because the northern data include certain interesting and significant regions like Japan and China, where the usual conditions are reversed. If equatorial regions were included in Figure 12, they would give an almost straight line. The connection between earthquakes and the seasons is so strong that almost no students of seismology question it, although they do not agree as to its cause. A meteorological hypothesis seems to be the only logical explanation. Wherever sufficient data are available, earthquakes appear to be most numerous when climatic conditions cause the Earth's surface to be most heavily loaded or to change its load most rapidly. The main factor in the loading is apparently atmospheric pressure. This acts in 2 ways. First, when the continents become cold in winter, the pressure increases. On an average, the air at sea level presses upon the Earth's surface at a rate of 14.7 pounds per square inch, or over a ton per square foot, and only a little short of 30 million tons per square mile. An average difference of 1 inch between the atmospheric pressure of summer and winter over 10 million square miles of the continent of Asia, for example, means the continent's load in winter is about 10 million tons heavier than in summer. Second, the changes in atmospheric pressure due to the passage of storms are relatively sharp and sudden. Hence they are probably more effective than the variations in the load from season to season. It is suggested by the rapidity with which the terrestrial response seems to follow the supposed solar cause of earthquakes. It is also suggested by the fact that violent storms are frequently followed by violent earthquakes. Earthquake weather, as Dr. Schlesinger suggests, is a common phrase in the typhoon regions of Japan, China, and East Indies. During tropical hurricanes, a change of pressure amounting to half an inch in 2 hours is common. On September 22, 1885, at Falls Point Lighthouse on the Bay of Bengal, the barometer fell about an inch in 6 hours, then nearly an inch and a half in not much over 2 hours, and finally rose fully 2 inches inside 2 hours. A drop of 2 inches in barometric pressure means that a load of about 2 million tons is removed from each square mile of land. The corresponding rise of pressure means the addition of a similar load. Such a storm, and to a less degree every other storm, strikes a blow upon the Earth's surface, first by removing millions of tons of pressure, and then by putting them on again. Such storms, as we have seen, are much more frequent and severe when sunspots are numerous than at other times. Moreover, as Vido long ago showed, one of the most noteworthy evidences of the connection between sunspots and the weather is a sudden increase of pressure in certain widely separated high-pressure areas. In most parts of the world, winter is not only the season of highest pressure and of most frequent changes of Vido's type, but also of severest storms. Hence, a meteorological hypothesis would lead to the expectation that earthquakes would occur more frequently in winter than in summer. On the Chinese coast, however, and also on the oceanic side of Japan, as well as in some more tropical regions. The chief storms come in summer in the form of typhoons. These are the places where earthquakes also are most abundant in summer. Thus, wherever we turn, storms and related barometric changes seem to be most frequent and severe at the very times when earthquakes are also most frequent. Figure 12 is displayed on the page, seasonal distribution of earthquakes, after Davison and Knott. Other meteorological factors, such as rain, snow, winds, and currents, probably have the same effect on earthquakes through their ability to load the Earth's crust. The coming of vegetation may also help. These agencies, however, appear to be of small importance compared with the storms. In high latitudes and in regions of abundant storminess, most of these factors generally combine with barometric pressure to produce frequent changes in the load of the Earth's crust, especially in winter. In low latitudes, on the other hand, there are few severe storms, and relatively little contrast in pressure and vegetation from season to season. There is no snow, and the amount of groundwater changes little. With this goes the twofold fact that there is no marked seasonal distribution of earthquakes, and that except in certain local volcanic areas, earthquakes appear to be rare. In proportion to the areas concerned, for example, there is little evidence of earthquakes in equatorial Africa and South America. The question of the reality of the connection between meteorological conditions and crustal movements is so important that every possible test should be applied. At the suggestion of Professor Schlesinger, we have looked up a very ingenious line of inquiry. During the last decades of the 19th century, a long series of extremely accurate observations of latitude discloses a fact which had previously been suspected but not demonstrated, namely that the Earth wobbles a little about its axis. The axis itself always points in the same direction, and since the Earth slides irregularly around it, the latitude of all parts of the Earth keeps changing. Chandler has shown that the wobbling thus induced consists of two parts. The first is the movement in a circle with a radius of about 15 feet, which is described in approximately 430 days. This so-called Illyrian movement is a normal gyroscopic motion, like the slow gyration of a spinning top. This depends on purely astronomical causes, and no terrestrial causes can stop it or eliminate it. The period appears to be constant, but there are certain puzzling irregularities. The usual amplitude of this movement, as Schlesinger puts it, is about 0 degrees 0.27, but twice in recent years has jumped to 0 degrees 0.40. Such a change could be accounted for by supposing that the Earth has received a severe blow or a series of milder blows tending in the same direction. These blows, which were originally suggested by Helmert, are most interesting in view of our suggestion as to the blows struck by storms. The second movement of the pole has a period of a year, and is roughly an ellipse whose longest radius is 14 feet and the shortest 4 feet. Or to put it technically, there is an annual term with a maximum amplitude of about 0 minutes 0.20. This, however, varies irregularly. The result is that the pole seems to wander over the Earth's surface in the spiral fashion illustrated in Figure 13. It was early suggested that this peculiar wandering of the pole in an annual period must be due to meteorological causes. Jeffries has investigated the matter exhaustively. He assumes certain reasonable values for the weight of air added or subtracted from different parts of the Earth's surface according to the seasons. He also considers the effect of precipitation, vegetation, and polar ice, and of variations of temperature and atmospheric pressure in their relation to movements of the ocean. Then he proceeds to compare all these with the actual wandering of the pole from 1907 to 1913. While it is as yet too early to say that any special movement of the pole was due to the specific meteorological conditions of any particular year, Jeffries' work makes it clear that meteorological causes, especially atmospheric pressure, are sufficient to cause the observed irregular wanderings. Slight wanderings may arise from various other sources, such as movements of the rocks when geological faults occur, or the rush of a crater rising from movements of the air. This fact, coupled with the mathematical certainty that meteorological phenomena must produce some wandering of the pole, has caused most astronomers to accept Jeffries' conclusion. If we follow their examples, we are led to conclude that changes in atmospheric pressure and in the other meteorological conditions strike blows which sometimes shift the Earth several feet from its normal position in respect to the axis. Figure 13 is displayed on the page. wandering on the pole from 1890 to 1898, after molten. If the foregoing reasoning is correct, the great and especially the sudden departures from the smooth gyroscopic circle described by the pole in the Eulerian motion would be expected to occur at about the same time as unusual earthquake activity. This brings us to an interesting inquiry made out by Milne and amplified by Knott. Taking Albrecht's representation of the irregular spiral-like motion of the pole, as given in Figure 13, they show that there is a preponderance of severe earthquakes at times when the direction of motion of the Earth in reference to its axis departs from the smooth Eulerian curve. A summary of their results is given in Table 9. The table indicates that during the period from 1892 to 1905, there were 9 different times when the curve of Figure 13 changed in its direction or was deflected by less than 10 degrees during a tenth of a year. In other words, during those periods, it did not curve as much as it ought according to the Eulerian movement. At such times, there were 179 world-shaking earthquakes, or an average of about 19.9 per tenth of a year. According to the other lines of Table 9, in 32 cases, the deflection during the tenth of the year was between 10 degrees and 25 degrees, while in 56 cases it was from 25 degrees to 40 degrees. During these periods, the curve remained close to the Eulerian path, and the world-shaking earthquakes averaged only 8.2 to 12.9. Then, when the deflection was high, that is, when meteorological conditions threw the Earth far out of its Eulerian course, the earthquakes were again numerous, the number rising to 23.4 when the deflection amounted to more than 55 degrees. Table 9 is displayed on the page, deflection of path of pole compared with earthquakes. In order to test this conclusion in another way, we have followed a suggestion of Professor Schlesinger. Under his advice, the Eulerian motion has been eliminated, and a new series of earthquake records has been compared with the remaining motions of the poles, which presumably arise largely from meteorological causes. For this purpose, use has been made of the very full records of earthquakes published under the auspices of the International Seismological Commission for the years 1903 to 1908. The only years for which they are available. These include every known shock of every description which was either recorded by seismographs or by direct observation in any part of the world. Each shock is given the same weight, no matter what its violence or how closely it follows another. The angle of deflection has been measured as Milne measured it, but since the Eulerian motion is eliminated, our zero is approximately the normal condition which would prevail if there were no meteorological complications. Dividing the deflections into 6 equal groups according to the size of the angle, we get the results shown in Table 10. Table 10 is displayed on the page. Earthquakes in 1903 to 1908 compared with the departures of the projected curve of the Earth's axis from the Eulerian position. Here where some 20,000 earthquakes are employed. The result agrees closely with that of Milne for a different series of years and for a much smaller number of earthquakes. So long as the path of the pole departs less than about 45 degrees from the smooth gyroscopic Eulerian path, the number of earthquakes is almost constant, about 8 1/4 per day. When the angle becomes large, however, the number increases by nearly 50%. Thus the work of Milne, Knott and Jeffries is confirmed by a new investigation. Apparently earthquakes and crustal movements are somehow related to sudden changes in the load imposed on the Earth's crust by meteorological conditions. This conclusion is quite as surprising to the authors as to the reader, perhaps more so. At the beginning of this investigation, we had no faith whatever in any important relation between climate and earthquakes. At its end, we are inclined to believe that the relation is close and important. It must not be supposed, however, that meteorological conditions are the cause of earthquakes and of movements of the Earth's crust. Even though the load that the climatic agencies can impose upon the Earth's crust runs into millions of tons per square mile, it is a trifle compared with what the crust is able to support. There is, however, a great difference between the cause and the occasion of a phenomenon. Suppose that a thick sheet of glass is placed under an increasing strain. If the strain is applied slowly enough, even so rigid a material as glass will ultimately bend rather than break. But suppose that while the tension is high, the glass is tapped. A gentle tap may be followed by a tiny crack. A series of little taps may be the signal for small cracks to spread in every direction. A few slightly harder taps may cause a whole sheet to break suddenly into many pieces. Yet even the hardest tap may be the merest trifle compared with the strong force which is keeping the glass in a state of strain and which will ultimately bend it if given time. The Earth as a whole appears to stand between steel and glass in rigidity. It is a matter of common observation that rocks stand high in this respect, and the consequent difficulty with which they can be bent without breaking. Because of the Earth's contraction, the crust endures a constant strain, which must gradually become enormous. This strain is increased by the fact that sediment is transferred from the lands to the borders of the sea, and there forms areas of thick accumulation. From this has arisen the doctrine of isostasy, or of the equalization of crustal pressure. An important illustration of this is the oceanward and equatorial creep which has been described in Chapter 11. There we saw that when the lands have once been raised to high levels, or when a shortening of the Earth's axis by contraction has increased the oceanic bulge at the equator, when the reverse has happened because of tidal retardation, the outer part of the Earth appears to creep slowly back towards a position of perfect isostatic adjustment. If the Sun had no influence upon the Earth, either direct or indirect, isostasy and other terrestrial processes might flex the Earth's crust so gradually that changes in the form and height of the lands would always take place slowly, even from the geological point of view. Thus erosion would usually be able to remove the rocks as rapidly as they were doomed above the general level. If this happens, mountains would be rare or unknown, and its climatic contrast would be far less marked than is actually the case on our Earth, where crustal movements have repeatedly been rapid enough to produce mountains. Nature's methods rarely allow so gradual an adjustment to the forces of isostasy. While the crust is under a strain, not only because of contraction, but because of changes in its load through the transference of sediments and a slow increase or decrease in the bulge at the equator, the atmosphere more or less persistently carries on the tapping process. The violence of that process varies greatly, and the variations depend largely on the severity of the climatic contrasts. If the main outlines of the cyclonic hypothesis are reliable, one of the first effects of a disturbance of the Sun's atmosphere is increased storminess upon the Earth. This is accompanied by increased intensity in almost every meteorological process. The most important effect, however, so far as the Earth's crust is concerned, would apparently be the rapid and intense changes of atmospheric pressure which would arise from the swift passage of one severe storm after another. Each storm would be a little tap on the tensely strained crust. Any single tap might be of little importance, even though it involved a change of 1 billion tons in the pressure on an area no larger than the state of Rhode Island. Yet a rapid and irregular succession of such taps might possibly cause the crust to crack, and finally to collapse in response to stresses arising from the shrinkage of the Earth. Another and perhaps more important effect of variations in storminess, and especially in the location of the stormy areas, would be an acceleration of erosion in some places and retardation elsewhere. A great increase in rainfall may almost denude the slopes of soil, while a diminution to the point where much of the vegetation dies off has a similar effect. If such changes should take place rapidly, great thicknesses of sediment might be concentrated in certain areas in a short time, thus disturbing the isostatic adjustment of the Earth's crust. This might set up a state of strain which would ultimately have to be relieved, thus perhaps initiating profound crustal movements. Changes in the load of the Earth's crust due to erosion and the deposition of sediment, no matter how rapid they may be from the geological standpoint, are slow compared with those due to changes in barometric pressure. A drop of an inch in barometric pressure is equivalent to the removal of about 5 inches of solid rock. Even under the most favorable circumstances, the removal of an average depth of 5 inches of rock or its equivalent in soil over millions of square miles would probably take several hundred years, while the removal of a similar load of air might occur in half a day or even a few hours. Thus, the erosion deposition due to climatic variations presumably play their part in crustal deformation chiefly by producing crustal stresses, while the storms, as it were, strike sharp, sudden blows. Suppose now that a prolonged period of worldwide mild climate, such as is described in Chapter 10, should permit an enormous accumulation of stresses due to contraction and tidal retardation. Suppose that then a sudden change of climate should produce a rapid shifting of the deep soil that had accumulated on the lands, with a corresponding localization and increase in strains. Suppose also that frequent and severe storms play their part, whether great or small, by producing an intensive tapping of the crust. In such a case, the ultimate collapse would be correspondingly great, as would be evident in the succeeding geological epoch. The seafloor might sink lower, the continents might be elevated, and mountain ranges might be shoved up along lines of special weakness. This is the story of the geological period as known to historical geology. The force that causes such movements would be the pull of gravity upon the crust surrounding the Earth's shrinking interior. Nevertheless, climatic changes might occasionally set the date when the gravitational pull would finally overcome inertia, and thus usher in the crustal movements that close old geological periods and inaugurate new ones. This, however, could occur only if the crust were under sufficient strain. As Lawson says in his discussion of the elastic rebound theory, the sudden shifts of the crust, which seem to be the underlying cause of earthquakes, can occur only after the accumulation of strain to a limit, and this accumulation involves a slow creep of the region affected. In the long periods between great earthquakes, the energy necessary for such shocks is being stored up in the rocks as elastic compression. If a period of intense storminess should occur when the Earth as a whole was in such a state of strain, the sudden release of the strains might lead to terrestrial changes which would alter the climate still further, making it more extreme, and perhaps preventing the storminess due to the solar disturbances to bring about glaciation. At the same time, if volcanic activity should increase, it would add its quota to the tendency toward glaciation. Nevertheless, it might easily happen that a very considerable amount of crustal movement would take place without causing a continental ice sheet or even a marked alpine ice sheet. Or again, if the strain in the Earth's crust had already been largely released through other agencies before the stormy period began, the climate might become severe enough to cause glaciation in high latitudes without leading to any very marked movements of the Earth's crust, as apparently happened in the mid-Silurian period. End of section 16. Section 17 of Climatic Changes, Their Nature and Causes by Ellsworth Huntington. This LibriVox recording is in the public domain, recorded by Leon Harvey. Conclusion. Here we must bring this study of the Earth's evolution to a close. Its fundamental principle has been that the present, if rightly understood, affords a full key to the past. With this as a guide, we have touched on many hypotheses, some essential and some unessential to the general line of thought. The first main hypothesis is that the Earth's present climatic variations are correlated with changes in the solar atmosphere. This is the keynote of the whole book. It is so well established, however, that it ranks as a theory rather than as an hypothesis. Next comes the hypothesis that variations in the solar atmosphere influence the Earth's climate chiefly by causing variations not only in temperature, but also in atmospheric pressure and thus in storminess, wind, and rainfall. This too is one of the essential foundations on which the rest of the book is built. But though this cyclonic hypothesis is still a matter of discussion, it seems to be based on strong evidence. These two hypotheses might lead us astray were they not balanced by another. This other is that many climatic conditions are due to purely terrestrial causes, such as the form and altitude of the lands, the degree to which the continents are united, the movement of ocean currents, the activity of volcanoes, and the composition of the atmosphere and the ocean. Only by combining the solar and the terrestrial can the truth be perceived. Finally, the last main hypothesis of this book holds that if the climatic conditions which now prevail at times of solar activity were magnified sufficiently, and if they occurred in conjunction with certain important terrestrial conditions, of which there is good evidence, they would produce most of the notable phenomena of glacial periods. For example, they would explain such puzzling conditions as the localization and periodicity of glaciation, the formation of loess, and the occurrence of glaciation in low latitudes during Permian and Proterozoic times. The converse of this is that, if the conditions which now prevail at times when the sun is relatively inactive should be intensified, that is the sun's atmosphere should become calmer than now, and the proper terrestrial conditions of topographic form and atmospheric composition should prevail, there would arise the mild climatic conditions which appear to have prevailed during the greater part of geological time. In short, there seems thus far to be no phase of the climate of the past which is not in harmony with an hypothesis which combines into a single unit the three main hypotheses of this book: solar, cyclonic, and terrestrial. Outside the main line of thought lie several other hypotheses. Several of these, as well as some of the main hypotheses, are discussed chiefly in Earth and Sun, but as they are given a practical application in this book, they deserve a place in this final summary. Each of these secondary hypotheses is in its way important, yet any or all may prove untrue without altering our main conclusions. This point cannot be too strongly emphasized, for there is always danger that difference of opinion as to minor hypotheses and even as to details may divert attention from the main point. Among the non-essential hypotheses is the idea that the Sun's atmosphere influences that of the Earth electrically as well as thermally. This idea is still so new that it has only just entered the stage of active discussion, and naturally the weight of opinion is against it. Although not necessarily the main purpose of this book, it plays a minor role in the chapter dealing with the relation of the Sun to other astronomical bodies. It also has a vital bearing on the further advance of the science of meteorology and the art of weather forecasting. Another secondary hypothesis holds that sunspots are set in motion by the planets. Whether the effect is gravitational or more probably electrical, or perhaps of some other sort, does not concern us at present, although the weight of evidence seems to point toward electronic emissions. This question, like that of the relative parts played by heat and electricity in terrestrial climatic changes, can be set aside for the moment. What does concern us is a third hypothesis, namely that if the planets really determine the periodicity of sunspots, even though not supplying the energy, the Sun in its flight through space must have been repeatedly and more strongly influenced by this, in the same way, by many other heavenly bodies. In that case, climatic changes, like those of the present, but sometimes greatly magnified, have presumably arisen because of the constantly changing position of the solar system in respect to other parts of the universe. Finally, the fourth of our secondary hypothesis postulates that at present, the date of movements of the Earth's crust is often determined by the fact that storms and other meteorological conditions keep changing the load upon first one part of the Earth's surface, then upon another. Thus, stresses that have accumulated in the Earth's isostatic shell during the preceding months are released. In somewhat the same way, epochs of extreme storminess and rapid erosion in the past may possibly have set the date for great movements of the Earth's crust. This hypothesis, like the other three in our secondary or non-essential group, is still so new that only the first steps have been taken in testing it, yet it seems to deserve careful study. In testing all the hypotheses here discussed, primary and secondary alike, the first necessity is a far greater amount of quantitative work. In this book, there has been a constant attempt to subject every hypothesis to the test of statistical facts of observation. Nevertheless, we have been breaking so much new ground that in many cases exact facts are not yet available, while in others they can be properly investigated only by specialists in physics, astronomy, or mathematics. In most cases, the next great step is to ascertain whether the forces here called upon are actually great enough to produce the observed results. Even though they act only as a means of releasing the far greater forces due to the contraction of the Earth and the Sun, they need to be rigidly tested as to their ability to play even this minor role. Still another line of study that cries aloud for research is a fuller comparison between earthquakes, on the one hand, and meteorological conditions, and the wandering of the poles on the other. Finally, an extremely interesting and hopeful quest is the determination of the positions and movements of additional stars and other celestial bodies, the faint and invisible as well as the bright, in order to ascertain the probable magnitude of their influence upon the Sun and thus upon the Earth at various times in the past and in the future. Perhaps we are even now approaching some star that will someday give rise to a period of climatic stresses like that of the 14th century, or possibly to a glacial epoch. Or perhaps the variations in others of the nearest stars, as well as Alpha Centauri, may show a close relation to changes in the Sun. Throughout this volume we have endeavored to discover new truth concerning the physical environment that has molded the evolution of all life. We have seen how delicate is the balance among the forces of nature, even though they be of the most stupendous magnitude. We have seen that a disturbance of this balance in one of the heavenly bodies may lead to profound changes in another far away. Yet during the billion years, more or less, of which we have knowledge, there appears never to have been a complete cataclysm involving the destruction of all life. One star after another, if our hypothesis is correct, has approached the solar system closely enough to set the atmosphere of the Sun in such commotion that great changes of climate have occurred upon the Earth. Yet never has the solar system passed so close to any other body, or changed in any other way sufficiently to blot out all living things. The effect of climatic changes has always been to alter the environment and therefore to destroy part of the life of a given time, but with this there has invariably gone a stimulus to other organic types. New adaptations have occurred, new lines of evolutionary progress have been initiated, and the net result has been greater organic diversity and richness. Temporarily a great change of climate may seem to retard evolution, but only for a moment as the geologist counts time. Then it becomes evident that the march of progress has actually been more rapid than usual. Thus the main periods of climatic stress are the most conspicuous milestones upon the upward path toward more varied adaptation. The end of each such period of stress has found the life of the world nearer to the higher mentality which reaches out to the utmost limits of space, of time, and of thought in the search for some explanation of the meaning of the universe. Each approach to the sun to other bodies, if such be the cause of the major climatic changes, has brought the organic world one step nearer to the solution of the greatest of all problems, the problem of whether there is a psychic goal beyond the mental goal toward which we are moving with ever-accelerating speed. Throughout the vast eons of geological time, the adjustment of force to force, of one body of matter to another, and of the physical environment to the organic response has been so delicate, and has tended so steadily toward the one main line of mental progress that there seems to be a purpose in it all. If the cosmic uniformity of climate continues to prevail, and if the uniformity is varied by changes as stimulating as those of the past, the imagination can scarcely picture the wonders of the future. In the course of millions or even billions of years, the development of mind and perhaps of soul may excel that of today as far as the highest known type of mentality excels the primitive plasma from which all life appears to have arisen. End of section 17, and the end of Climatic Changes, the Nature and Causes by Ellsworth Huntington. This is a LibriVox recording. All LibriVox recordings are in the public domain. Recorded by Leon Harvey for LibriVox.org.